In electronics projects, it's common to use a microcontroller board, like an Arduino or a Raspberry Pi, to control other devices, turning them on or off. But using an Arduino to control something else, like an electric motor, is a bit more complicated than simply connecting it to the Arduino's digital output pins. For one, the motor probably requires a different voltage than the Arduino's output. My little DC motor is designed to operate at 6 volts, but my Arduino only outputs a 5-volt signal. Another problem is that the amount of output current that an Arduino board can produce is probably a lot less than I need to power my motor. What I need here is for the motor to get its power from a dedicated 6-volt power supply, but I need the Arduino to control when it's on or off. To do that, I can use the transistor as an electrically controlled switch to interface between the two components and enable the Arduino to turn the power on or off to the motor. Unlike a mechanical switch, which contains parts that physically move to open or close a circuit, a transistor switch is turned on or off electronically by controlling the voltage and current at the transistor's base terminal to put it in either the saturation or the cutoff mode. When the transistor is in the saturation mode, it'll act like a closed switch to turn on whatever device is connected to its output. And when the transistor is in the cutoff mode, it'll act like an open switch, which turns off the connected device. To use an NPN transistor as a switch, I'll connect the source of my control signal to the base of the transistor, and to limit the amount of current that the transistor draws from the controlling device when it's turned on, I'll include a resistor in series between the base and control signal source. Next, I'll tie the emitter terminal to a low fixed voltage, which is almost always ground, and I'll connect the collector pin to the device I want to control power to, which will be connected to its power source on the other side as shown here. Since this circuit will be switching a motor on and off, and motors tend to act as an inductive load, I'll also include a flyback diode here to protect my circuit from potentially damaging flyback voltage spikes. To turn this motor on, all I need to do is raise the control voltage enough so that the base emitter junction turns on, which is usually around 0.7 volts, and then provide enough current into the base to saturate the transistor. When it's saturated, the transistor acts similar to a short circuit between the collector and emitter, which is like a closed switch. The motor's turned on, and it draws current from the 6-volt power supply. To turn the motor off, I simply lower the control signal down to ground, which means the voltage between the base and emitter will be less than the threshold to turn on the transistor. The transistor will be in the cutoff mode, where it acts like an open switch to prevent current from flowing through the motor. Most microcontroller devices, like an Arduino or Raspberry Pi, output digital signals that switch between 0 volts to represent a low value and 3.3 or 5 volts to represent a digital high value. And those voltages work great for toggling a bipolar junction transistor switch on or off. However, the output pins on a microcontroller board are usually only designed to output a small amount of current, and if the transistor tries to draw more current than it can handle, that might damage the controller. When the transistor is turned on, the junction between the base and emitter acts like a forward bias diode, which allows current to flow freely into the base. And that's why it's important to include a limiting resistor between the source of the control signal and the base terminal. Without that limiting resistor there, the transistor might try to draw more current than the attached controlling device can provide. So this resistor serves a similar purpose to the current limiting resistor connected in series with a light emitting diode. As a rule of thumb, for most microcontroller-based hobby projects, 1 kiloohm is a good value to use for the current limiting resistor. If I connect this circuit to the digital output line of an Arduino microcontroller, which outputs 5 volts to represent digital high, 0.7 volts of that will be dropped between the transistor's base and emitter terminals, which leaves 4.3 volts to be dropped across the 1 kiloohm resistor. According to Ohm's law, 4.3 volts dropped across a 1 kiloohm resistor will only draw 4.3 milliamps from the Arduino, which is well within the current output capabilities of my little Arduino microcontroller board. The other current that I need to consider is the current between the collector and the emitter. When the transistor is switched on, all of the current going through the motor will flow into the collector terminal and pass through the transistor. So I need to make sure that I select a transistor that can dissipate enough power to handle that much collector current. The amount of current through an electric motor is based on the applied voltage across the motor and its internal resistance. For a simple example, I'll treat that motor as if it's a 100 ohm resistor in series with an inductor. When the transistor is turned on and saturated, there will be a 0.2 volt drop between the collector and emitter terminals, which leaves 5.8 volts to be dropped across the motor coming from its 6 volt power source. According to Ohm's law, 5.8 volts across a 100 ohm resistor allows 58 milliamps of current to flow into the transistor's collector. If I'm using a 2N3904 BJT, which can handle a continuous collector current of 200 milliamps, then this circuit should work just fine. If you're using a transistor to switch other types of load devices, you'll need to consider that device's unique current characteristics to make sure your transistor can handle it. Now, to demonstrate this circuit, I've written a simple Arduino program that repeatedly toggles digital output pin 0 between its high state and its low state about once every second. I've included the program in the exercise files as transistor switch arduinodemo.ino if you want to use it as reference. I've connected that control signal from pin 0 of my Arduino to the base of my NPN transistor, and I'm using my oscilloscope to display that signal on channel 1 in yellow. My benchtop power supply is providing 6 volts through the breadboard power bus to power the motor, which is connected to the transistor's collector terminal. Looking at the oscilloscope, I can see that when the Arduino output goes high, the transistor switch turns on and the motor spins. And when the Arduino's output is low, the transistor switch is off, so the motor stays still. This type of circuit is called a low side switch because the NPN transistor is on the low or ground side of the device it's controlling. If I wanted to switch the polarity of the control signal so that my transistor switch turns on when the control voltage is low and off when it's high, I'll use a PNP transistor instead. But to use a PNP transistor, I'll need to create a high side switch. As with the NPN low side switch, the control signal is connected to the PNP transistor's base with a resistor in series. I've connected the PNP's emitter terminal to a constant voltage, but this time it's the high voltage from the power supply. And the motor I'm controlling is connected on the low side between the PNP's collector pin and ground. The input voltages I use to control a PNP high side switch are the opposite of the control signals for an NPN low side switch. To turn the switch on, I'll need to provide a high voltage control signal if I'm using the NPN switch, and a low voltage signal for the PNP switch. And to turn the switch off, the NPN switch requires a low input signal, whereas the PNP switch needs a high input. As long as my controlling device can produce the necessary high and low control voltages, a PNP switch will work just as well as its NPN counterpart. But it may not always be possible to produce those required voltages. One potential challenge of using the high side PNP switch is that for it to turn off, the control voltage needs to be high enough that the voltage between the base and emitter is less than the 0.7 volt threshold. If I was using an Arduino to control the circuit shown here, since the Arduino's high output signal is only 5 volts, but the motor's power source is connected to 6 volts, my Arduino can't produce a high enough voltage to turn this switch off. This switch will forever be stuck on. However, if the supply voltage for the motor was lower, let's say just 5 volts, then the PNP switch would work just fine. This relationship between the control and supply voltages is important to consider when choosing whether to use an NPN or PNP transistor switch. In general, I tend to use NPN low side switches more often than their PNP high side counterpart because I know I can always control it with an Arduino or a Raspberry Pi, regardless of the supply voltage that's connected to the load.